All right, so I'll quickly introduce OpenCue, and I'll be passing the word for Graham from beloFX to present their work on OpenCue integrating it into the cloud. So I'm Diego Tavares. I'm a lead software engineer at Imageworks, and I'm also the chair for the OpenCue project, TSC. And OpenCue is an open source render farm management system for distributing VFX and animation workloads across cluster computing environments. It not only allows distributing the work on a cluster, but also maintaining the cluster and balancing resources between different shows that are running jobs on the cluster. And OpenCue was initially developed 21 years ago, and it was simply named Q at Imageworks. And in 2019, it was open sourced, and it became a member of the ESWF. And last year, Matt Chambers, which was the founder of OpenCue, the guy who initially developed it, got awarded a site tech, and is running on OpenCue. OpenCue is running on Imageworks since 2020. I was lucky enough to be tasked for deploying OpenCue on our render farm system, and it was a challenge to migrate a whole facility to a new environment, but it has been used since 2020 to produce all the movies that are listed here. And today we have last year we had a total of 15 contributors, 15 companies contributing to OpenCue, a total of 44 contributors, individual contributors to our repo. And the project has been healthy and been used by several studios so far. And that was all from me. I'll pass the word to Graham on the video.
Okay, hi everyone in Denver. I hope you're having fun, and I'm sorry I'm not there in person. Thanks a lot to Diego for facilitating this virtual talk, and of course for all the hard work on OpenCue. So I'm going to talk a little bit about how we've implemented OpenCue at beloFX, and I'll talk about some of the challenges that we've had, what we've done to resolve them, and some of the decision making that we made along the way. It's going to be a sort of fairly high-level talk because we have a huge amount of time, but I will kind of get into a little bit of the sort of technical details of the cloud setup that we have. So I hope that's okay for everyone. So first, a quick intro. Obviously, you've already met Diego. Thank you very much, Diego. I'm Graham Jack. I've been working in the visual effects industry for a long time. I was at DNEG for about 20 years or so. And about 3 years ago, we started a little visual effects company called beloFX, which is where I am now. So I guess I'll start with a little bit of background on beloFX. Like I say, we started up about 3 years ago in 2021. And we knew when we were getting started that we wanted to be able to work in a bunch of different locations, partly because there were great people that we really liked working with in places like Vancouver, but also obviously because we needed to respond to our clients' needs in terms of tax credits and where they wanted us to be working. So because of this idea of being a small startup company but trying to get going globally as quickly as we could, we made the decision to kind of get started as a cloud-only setup, just as a way to maintain some agility while we were first getting going. And that decision has obviously informed a lot of thinking around the technical setup generally, but also specifically around the render farm setup. So that is what I'm going to dive into. So we sort of started thinking about render farm, we started thinking about our requirements, and I think the key point that we focused on was this idea of scalability. So the only way you can make it even vaguely financially viable to do your rendering in the cloud is if you're scaling those resources up and down very, very efficiently. And I think particularly because we knew that as a smaller, newer company, we weren't going to have, lots of shows running all at the same time where you can balance your workload. We knew it was going to be really spiky. So we needed something that was designed to kind of accommodate that sort of dynamic scaling. Also, on the sort of financial side of things, we knew that we were going to have to use spot instances or preemptible instances. So any system that we use had to be robust enough to deal with render nodes getting killed with no notice. And obviously, we wanted something where we could, it could be as flexible as possible. We didn't necessarily want to commit to, a specific type or size of node. We knew that we might want to be using GPUs because of the technology that we were using. So having some kind of flexibility was important too. So with that in mind, why did we choose OpenCue rather than something off the shelf? Loads of people use off the shelf rendering software. And I think the first thing really was that we wanted something where we had a lot of control. We are a fairly technical company. A lot of the key people kind of know their way around fairly technical software. So, and we knew that our setup was going to be a little bit different. So we thought it might end up needing a fair bit of customization. We also were keen not to be tied too much to a specific cloud provider. And it felt like quite a lot of the commercial rendering software was going in that direction, either towards Amazon or Azure or whatever. And also, personally, I'm pretty passionate about the use of open source software in our industry and the ASWF in particular. So it appealed to me to use a project from the ASWF. And then I guess the last point in terms of rendering software, it was pretty reassuring to know that we were using something that could handle the kind of load that rendering something like a Spider-Verse movie must have generated. So all of those things kind of contributed to us sort of at least deciding to do a kind of initial proof of concept with OpenCue. So just as a recap on the OpenCue architecture, or for anyone who's not familiar with it, you've got this backend database which tracks all your hosts and jobs. You've got one or more of these QBot instances, which is a Java application that handles all of the orchestration. And then the render nodes themselves are running the RQD daemon, which communicates with QBot to accept jobs and things like that. And then on the artist side, you have QGUI and QCommander to monitor the jobs, see what's going on. You've got some render dispatchers built on top of PyOutline. And then you've got this Python library, PyQ, which is gluing everything together and letting those Python applications communicate with the backend. And in a sort of conventional setup, you'd probably have Blade server or something like that in your render farm, that each node of which is running an RQD instance, and then your database and your QBot instance running on a server of some kind. This was our initial cloud implementation. So I'll kind of talk through what each of these sort of represents in our world. Like I said, the key thing was that we needed this ability to scale the render nodes up and down very flexibly. And so rather than reinvent the wheel when it comes to that scaling side of things, we decided to investigate using Kubernetes for the orchestration. And in particular, since we got started using Google Cloud, we used Google's Managed Kubernetes Service, GKE. So in our world, the artist workstations are virtual machines in Google Cloud. The database on the back end is Google Cloud SQL, and then everything else lives in Kubernetes. So the render nodes themselves are different types of render pod for different applications, which are running on different node pools. So the node pools can be customized as needed. And then all of the node pools have cluster auto-scaling turned on. So if there isn't a pod to schedule on the node pool, it deletes the underlying VMs. And then Qbot itself is another pod which is running on our main node pool. And then we have the metrics service, which is was at the for our kind of initial implementation was pretty much just the vanilla Prometheus metrics collector that you'll find in the OpenCue repo, and that was sending metrics to our Prometheus instance. All the render pods were configured with a horizontal pod autoscaler, which is a kind of native Kubernetes resource type, which can increase and decrease the number of pods based on some kind of metric. And just for anyone who doesn't know what a pod is in Kubernetes, it's a kind of base entity which can run one or more containers, and it can manage things like disk mounts, environment variables, and things like that. And this setup worked well for us as a proof of concept, but we did have a few issues with it. So I'll go into kind of what those issues were. So most of the initial challenges that we faced were really based around the scaling side of things. So for the proof of concept, we just used CPU-based scaling because it's very easy to set up with just the basic horizontal pod autoscalers in Kubernetes. So the sort of basic logic was if the whole of the render nodes within a particular node pool for a type of render were maxing out on CPU, then the node pool would scale up until it's not maxing out anymore. Obviously, up to a given limit that you set. Now, of course, there can be lots of different reasons why CPU isn't being maxed out, like I/O weight or things like that. So that's not necessarily the best way of doing things. So in order to kind of get something working, we had to add various delays and buffers and things like that so that it wouldn't scale down if there was a short period where the CPU wasn't maxed out. Another issue that we had was that because the pods in Kubernetes don't get well-defined host names that they can be reached at, we had it set up so that OpenCue would register them using their IP address, which is a setting that you can set within OpenCue. But as the nodes scale up and down, particularly if you've got a lot of very dynamic scaling, the IP addresses can get recycled. And if that happens before they're cleared out of OpenQue's database, then OpenCue can get confused and think that they're a different node type and end up trying to run nuke jobs on Arnold nodes or something like that. Another point on the scaling. Somebody clever once said that when you start moving to the cloud, you should think of servers as cattle rather than pets, i.e. you should expect them to be killed without notice, and you should set your systems up to deal with that. But in a render farm setup, because you might have invested a bunch of render time already on a particular node. They might be cattle, but they're like really expensive cattle, like Kobe beef or something like that. And because when Kubernetes scales nodes down, it's respecting the pods as cattle mantra. It's indiscriminate in the way that it kills those nodes to scale back down. So, if you're going from 15 nodes to 10 nodes, the 5 that gets killed could happen to be the one that your long-running renders are on, which is obviously a problem. And then lastly, you obviously get other constraints on how many render nodes you want to be running. Things like server load or the number of software licenses that you own. These can change quite dynamically, so you need some easy way to control the scaling and how far things can scale. But this setup worked really well as a proof of concept, and it let us test things like sort of robustness testing. So we would go in and just randomly kill a bunch of pods, randomly kill the actual Qbot nodes themselves and things like that. And we were really pleased by how robust this combination of OpenCue and Kubernetes was. Basically, whatever we did, the nodes would get restarted, the services would restart, and everything would just pick up from where it left off before the nodes were killed. So that was really encouraging. So this kind of represents the next iteration of our setup. So we added a bunch of things. The first thing we did was we added this admission webhook to the actual render node deployments. So in Kubernetes, admission webhook is a webhook that can get called as resources get created, so you can modify them as they're being created. And I think there's lots of things that we might end up wanting to do with this, but at the moment, what we do is we use it to set the host name of each pod to match the underlying node type that it's running on. So the nodes can now get registered in OpenCue with a sensible host name and reached at that host name. We also added something called CADA, which stands for Kubernetes Event-Driven Autoscaling, which is a really nice open source project, which I believe has now been incorporated into Kubernetes itself to let you scale based on custom metrics from anywhere you want, in our case, from Prometheus. And it's a really nice implementation because it uses all of the underlying Kubernetes primitives. It's not trying to reinvent the wheel. It's just an extra layer that you add on to give you some more flexibility. And an important point is that it allows the node pools to scale down to 0, which is important to us. The sort of basic auto-scaling in Kubernetes only let you scale down to a single node, but obviously having a large render node hanging around when you don't need it is a cost that we don't want. So that kind of full scaling to 0 was important to us. And so the way that works for us is we generate a specific metric that goes to Prometheus that we call cores required, which is pretty self-explanatory. And that's sort of calculated by the length of the render queue for a given render type, as well as things like what jobs are already running on hosts and things like that. So that was driving the scaling, and CADA then talks to the autoscalers to turn them on and off and set the limits. And then we also added this additional Python service, which we called the OpenCue controller. And this does a few things for us. Firstly, it creates and it updates and maintains an annotation on the render pods, which is called shutdown cost. And this is something that was added in a sort of more recent version of Kubernetes, which essentially tells the Kubernetes API, it gives it some insight into the cost of killing a given node, so that it can use that to decide the order to kill nodes as it scales down. And so we grab metrics from OpenCue to drive this, and it's basically based on the longest runtime on each host, so on each pod. So essentially, the longer running a render is on a particular pod, the higher the cost of killing that pod. The other thing the service can do is it communicates with the CADA scaled object resources and can set or check the limits of those, and it exposes a simple API to do this so that we can write tools around it to be able to update the scaling limits. And we recently added the ability for these controller objects to communicate with each other across clusters, so that we can end up with a kind of sort of meta scaling where we can balance limits between clusters. So if you have say a fixed pool of global licenses that you need to work within, you can scale one site up if there's a lot of demand there, and scale the other one down simultaneously to sort of stay within that license limit. So that's something that's been really useful to us. So just a few details about the actual implementation itself, and some of the tools that we use to do that. So we use Terraform to define all of the primitives, so including the clusters themselves, the Cloud SQL database, all of the DNS and things like that. Then each sort of type of thing that's going to get deployed into Kubernetes onto the clusters themselves is a Helm template. So for anyone who doesn't know, Helm is a bit like a package manager for Kubernetes, where you can create templates for different resource types and package them up. And then for the actual instances of those things, we use something called Helm file, which lets you define in a declarative way a bunch of resources based on those Helm templates with different values. So for example, we have an RQD Helm template, which is used to, which defines essentially an RQD deployment with a particular image type and the scalars and scaled objects that go along with that. And then we deploy instances of that using Helm file for Houdini, Arnold, Nuke, etc., each of which has its own set of values that define how it gets registered with OpenCue, which actual render image it's running, and things like that. And then things like Qbot and the controller are Helm templates in themselves, which also get deployed through Helm file. So in terms of the actual underlying compute nodes themselves, we create different node pools for different types of render so that we can right size them for the task at hand. So for example, something like Arnold, which scales really well, can have lots of CPUs as well as lots of RAM, whereas something like Nuke, which might not scale quite as well with the number of cores, we can have the RAM but less cores. And obviously, as discussed earlier, everything is a spot instance on GKE to manage the costs. So just a few thoughts on future work, things that we'd like to do if we get the time. One thing we'd like to do is re-implement the way things work as a Kubernetes operator. So for those of you who don't know, an operator in Kubernetes lets you define custom resource types, and then the operator responds to those resources by creating the underlying bits and pieces in Kubernetes. So we thought it might be more intuitive to have a specific resource description for an RQD node type, be able to list those as separate resources and things. We feel like we could do with a dedicated GUI to be able to see the size of all the node pools and shift limits around, and maybe integrate a kind of higher level view of things than what QCommander gives. We're currently working on a sort of quota system to make it easier to track and control resources against specific shows or sequences or whatever, so that we can attribute compute costs to those things and monitor the kind of burn down against the budget. We've already got a bunch of alerting based on the kind of underlying services, but we need something that's a little bit more artist focused to warn users about bad renders and things like that. We gather lots of metrics. It all goes into Prometheus. We also scrape all of the logs to Loki, but at the moment we're not really doing much with it, and we'd like to use a lot of that to get better at forecasting future usage. And then the last one is kind of a bit of an open question, really. We've kind of been asking ourselves, what does a real Kubernetes render queuing system look like? There's a lot of crossover between what OpenCue does and what Kubernetes wants to do in terms of packing jobs onto nodes and things like that. So we've been wondering if there's a better hybrid of the two that would kind of fit in better with the Kubernetes paradigm, but still present a familiar experience to people used to working with render farms. But that's probably a talk in itself. So just to wrap up, OpenQue's worked really well for us so far. We've actually done very minimal work on OpenCue itself. We've just added the ability to work with fully qualified host names and made a few changes to the way things get logged. But most of what we've done has been the scaffolding surrounding it and the Kubernetes framework. So yeah, huge thank you to everyone who's contributed to the project, and in particular, the TSC who've been managing the work. And big thank you to everyone for listening. Thank you very much.
And as for the latest project updates and what is coming soon for OpenCue, we had a presentation on last Thursday on our virtual town hall, and the recording is available on YouTube. So feel free to go there and watch. And I'm losing my voice, sorry. Thanks, everyone. That's it.